the previous lecture, we were talking about behavior trees. And so we're going to look a little bit at the implementation now of so how you might implement a behavior tree. There's a bunch of details here that I'm not telling you about them. So if you're actually trying to do this in a video game, you need to read a little bit more about them. You also need to know a little bit more about things like threading and stuff like that. So what I'm going to tell you today works only when you're implementing very simple actions or very simple composite actions, but it's not going to work for you in general. So if you're going to try to do this sort of thing in a real game, so I'd recommend that you either use the built-in behavior tree in your game engine or you use a pre-made one. When you go to look at implementing your own, should you choose to do so, you do need to be aware that there are other issues that I'm not touching on in the lectures. All right, so this is what our behavior tree, if you were to draw a UML diagram describing the different types of tasks in a behavior tree, you'd come up with something like this. Right? And so our tasks in our tree, you would probably implement them as either an interface or an abstract class. Right? All tasks are, well, they're tasks. So conditions and actions, they're just tasks. So you would subclass task, and these would be abstract as well. Now the reason they're abstract is because you're going to specialize these, right? You're going to have to make some condition that you want to test, right? So you want to test, are you within some proximity of something? So you have to subclass this class here to make a concrete condition. Similarly, for your action, you might want an action that walks across the map or something like that. You're going to subclass this to make a concrete action that actually walks across the map. Right? Our composite actions, well, they're abstract as well because you can't just have a composite, right? It has to be one of a selector or a sequence. Right? Of course, if you generalize this sort of thing, you can make different types of composite tasks as well. Right? Your selector and sequence, however, these can be concrete classes. So these can be actual fully implemented classes because it turns out that the methods that you need in selector and sequence are easy to implement. The nice thing, one of the big reasons behavior trees have become popular is because all tasks have the same interface. Right? You might have noticed that when you were implementing or working on assignment 2, depending on how you approach the problem, you might have run into a situation where different states would require they'd have different interfaces. You might need extra methods or they might need extra information that other states don't need. So you might have run into that issue, you may not have. But the nice thing here is that all tasks, they have the same interface. So programming or using them is relatively easy. Okay, so what methods would you want to put, should every task have? Right, and so a task should be able to run. An individual task should be able to run. Right? So you've got some tasks like walk across the map, the run method would walk across the map. Right? Whatever steps you need to walk across the map, you would put into run. Remember our tasks, every task has a status, right? Either the task is running or it's complete. If it's complete, then it's either failed or succeeded. So our getStatus method would return the current status of the task. All right, so what does composite look like? Well, remember a composite manages a bunch of child tasks. So inside a composite, there's going to be a list or an array or something, a set of children. Right here I'm just using an array because that's the easiest thing to write, but you could use some other collection here. Right? So every composite has a bunch of children tasks, has a bunch of child tasks. Right? And selector, you can actually go and implement. So this is just pseudocode. This is some hybrid, this is just some made up language, right? It's basically pseudocode. Kind of looks like Java, kind of looks like something else. Right? So remember what a selector does, right? So when you run a selector, it runs its child tasks in sequence. Right? Runs the first one, then runs the second one, runs the third one. Right? And a selector chooses the first child task that succeeds. Right? So conceptually, all you need to do to implement this method is to run each child. Right? So for each child that the selector task has, right? Run the child. Right? This is where you get into trouble in these behavior trees. Right? So if this run step here is slow or takes some amount of time, this is where you run into problems. Which is why there's a question mark in the next on the next line, right? And so while the child's status is running, so while it's doing something, you have to decide what you're going to do inside your behavior tree. Remember, you're implementing the behavior tree because you want to choose an action for something under your control, or sorry, something under the AI's control, right? And so if this task is taking a long time to finish, you're not going to be able to control you're not going to be able to control whatever game object it is you're trying to control until this task finishes running. You don't want that to happen, right? So here you probably don't want to wait for the child task to finish. You want to do something else. And this is why you probably want to introduce threading into your tree. Anyway, conceptually, that's what you're going to do, right? And then if you find a child task whose status succeeds, or a child task that succeeds when it runs, then you're done, right? So you can record the status as being success, and you can return. And of course, back here, get status is just going to return, whatever this value stored in status is. Right? If you process all of the child tasks and none of them succeed, then a selector fails. Right? And so now you'll set the status to failure, and when someone calls get status, you'll return failure. Selectors and sequences, basically the code's the same. Right? Remember, in a sequence task runs all of its child tasks in order, right? Until it wants to run them all. If one fails, then the sequence is considered to fail, right? So again, for each child in the children, run each child task, right? Let's assume the child task finishes immediately, so we now check its status, right? And so if the status is failure, we know that the overall status of the sequence is to fail. Right? If you can process all the child tasks and they all succeed, then you know the overall status of the sequence is success. Right? You've performed every child task that the sequence wanted to run. Okay, so conceptually that's pretty straightforward, right? And so you can actually get pretty far just using a design like this, right? You can get surprisingly far. But eventually you'll realize that, hey, there's other things you want to do that you can't capture with this simple model here. Right? So for example, you spend a lot of time designing and implementing some really complicated sequence or selection, right? So you build a subtree in your tree, right? And you end up with some amazing sequence here, right? And now you decide, hey, look, I want to run this thing 3 times. So how do I do this now, right? So how do I run something n times, or 3 times in this case? Right? And so you sit and you think for a little bit and you say, well, one way to run a sequence 3 times is to create another sequence node task and have 3 child tasks that are all your amazing sequences, right? And so that would be the quote unquote obvious solution, right? And so you do something like this, right? So you create a new sequence node or task, sorry, right? And its 3 children are your amazing sequences, right? And so this would work, right? It would work. What are the disadvantages? Well, you've now got 3 copies of your amazing sequence in your tree. That seems wasteful, right? One of the reasons that you create a behavior tree is to create reusable behaviors. Now I'm repeating or copying a behavior 3 times because I want to run it 3 times. So that seems kind of wasteful. And more generally, if you don't know how many times you want to run your sequence, but you know you want to run it n times, so imagine that you compute something in your game at runtime, you come up with some value n, and you say, I'd like to run this sequence n times, you've got no way to do it, right? You make your behavior trees before you run your program, right? And so there's no way for you to add or create a node and put in n copies of a sequence at runtime. And so that's a little annoying. I shouldn't say you can't do it. So certain implementations of behavior trees, you certainly could. But a typical implementation of a behavior tree, you would not be able to modify at runtime. Right? And so now you ask, well, okay, so how do I run this sequence n times? Conceptually, it's straightforward. You need a loop, right? I want a loop. I want to run the sequence n times. So conceptually, it's very straightforward. But with our hierarchy of classes, we can't do it. So there is a possible solution to this. Right? So a possible solution to this is, this is what a new-ish object-oriented programmer would do, right? So someone who doesn't have a ton of experience programming, right? They would say, well, look, we've got this class called sequence, right? I'm working in an object-oriented programming language, so I can subclass sequence, right? And so I can make a repeating sequence, right? And this, in fact, does solve your problem, right? You can easily subclass sequence. You can make repeating sequence. Inside repeating sequence, its run method basically has a loop that runs your sequence n times, right? Easy peasy. So this works, and this seems like a solution. So you carry on, and eventually, some later time, you've got some amazing action that you've created, right? Amazing action could be, it could be a subtree somewhere, right? There could be a bunch of other things underneath here. And now you ask yourself, well, how do I run this action 3 times, right? And so you could do this again, right? So make a selector, make a sequence node, right? Have 3 amazing actions under it, right? And now you ask yourself, well, okay, so how do I run this n times, right? And you could play the same trick, right? You say, well, I can just subclass amazing action, right? And have repeating amazing action, right? Repeating amazing action, it's got a constructor, it takes in a value of n, right? Inside its run method, it runs your action n times. This is great, right? Until you realize, right, you start creating more actions and you realize, hey, I would like to repeat my another action n times. So now I have to subclass that too, right? You make yet another action and you realize, well, I have to subclass that now too, and so on, and so on, and so on. And this is just to run something n times, right? You can imagine doing something else where one solution would be, well, I can just subclass my action or subclass my task and to create the class that's required, right? But every time you want to do something that's the same, you have to subclass again, and that is not sustainable, right? And so it would be nice if there was some other solution for this. It would also, it should also be obvious to, well, it shouldn't be obvious. So it might also occur to you that this is not an uncommon problem when you work in an object-oriented programming language, right? This sort of thing probably happens in not just games, but everywhere else where object-oriented programming is common, right? And so that's what the decorator pattern is for. So this is yet another one of these gang of 4 patterns, right? So remember, state is a gang of 4 pattern, right? Decorator, another one of the patterns that they talked about. Right? And so if you look up the decorator pattern on Wikipedia, it tells you the decorator pattern provides a flexible alternative to subclassing for extending functionality, right? We're subclassing to extend functionality, right? So when using subclassing, different subclasses extend a class in different ways. Okay, so repeating another action, subclasses another action so that you can repeat the action n times, right? However, an extension is bound to the class at compile time and can't be changed at runtime, right? And so in other words, yes, you can make a repeating another action, right? But you have to do that you have to do that at compile time, right? So in other words, you have to write the code for it beforehand, right? There's no way that I can take an existing another action and repeat it, right? Without subclassing in this solution, right? The decorator pattern allows responsibilities to be added and removed from an object dynamically at runtime, right? And so this looks like it's a possible solution for us. There's something here that's missing. So you can add a responsibility, but it turns out you can add multiple responsibilities. So it turns out you can add multiple decorators to a class and extend it many different times, right? And extend its functionality in many different ways, right? So in other words, this is a layered pattern. And so this is what it looks like. So the problem with the Gang of 4 book is that you get pictures like this. They're very abstract. They describe the pattern succinctly, right? But the problem is to apply these sort of things, you kind of, you have to play around with them. Or someone has to explain to you how they actually work. So if you just look at this thing, it's not obvious what the heck's going on here. So here's our component. So this is the thing that I want to, Here's component, so it's abstract. So it's an abstract class or an interface of some kind, right? It provides one or more public methods, right? So operation is the one public method that this component has. So you can make a concrete component. So in our case, this might be action, and this is going to be task. But let's step back for a minute and say this could be action. This could be our walk action. So this is your concrete implementation of an action, right? It overrides operation. So in other words, in our example, it would override run so that when you run your walk action, it walks across the map. Right? I would like to extend this action. In our case, I want to do it. I want to be able to repeat the action n times. Right? And so what you do here is there's your concrete component. You now create another subclass called decorator. It's also abstract. Right? And so the way this thing works is that it has a field inside of it that is a reference to a component. So in this example, it's going to be a reference to your concrete component. Right? And so how do you set that reference? Well, the decorator constructor is going to take in a component as one of its arguments. You're going to set your component field to point to the actual component. So in our case, our decorators are going to have a reference to a task object. Right? And now, every public method in your component, you repeat in the decorator class. Right? And so in other words, the decorator object has the exact same interface as the component. Right? The exact same public interface as the component. Every operation in your decorator class simply says component.operation. Right? So if there's a run method here, we would implement the operation in the decorator class as component.run. Right? You just forward the run request to the underlying component. Okay, and now you have your concrete decorators. So these are the classes that actually add the functionality that you're trying to add. Right? They override any of the methods that they need to override, and they provide a new implementation of the operation. Except it's not really a new implementation now, it's an extra thing that you can do. Right? And so I'll show you exactly what this means in a second. So in your concrete decorators, you override the action. In the decorator class itself, you simply forward the call to the method to the underlying component. Right? Now again, you look at this thing and you say, well, I have no idea how this solves the problem. Right? Okay, so let's look at an example. So this is a simple example using a decorator. So here I've got a class called coffee. It's abstract. Right? It represents something that you can drink. Right? Black coffee is my concrete class. Right? It represents the simplest type of coffee that you can drink. Here's my coffee decorator. Right? Internally, it has a reference to a coffee object. Right? And so I'm going to call that field drink. Right? So how can you decorate a cup of coffee? Well, I can put some foam on it, or I can add some milk to it, I can put some sugar in it, and so on and so on and so on. Right? I haven't been to Starbucks in a long time. There's probably a bazillion other things you can add to your coffee now. Right? And this would be an example of using the decorator class. So let's go ahead and implement this. So I'm going to do this in Java. So here's coffee. Right here. Right. So coffee is an abstract class. Right. It can have whatever fields are common to all types of coffee. Right. I don't really care about the fields for the purposes of this example. Right. But it does have a method. Right. It could have multiple methods. Here we're just going to work with one. Right. And so there's a drink method. Okay. So we need to make. Where's my picture? Okay, so I need to make a black coffee class that is a concrete implementation of coffee. Right, so let's do that. So over here, new class. So black coffee. Its superclass is coffee. Right, so our black coffee class extends the coffee class, right? Our drink method, I'm just going to do, I'm just going to print out something. So I'm just going to say drinking coffee, like that. Right? Okay, so now in our decorator class, right? So our decorator class, right? It's an abstract class, right? It's a subclass of coffee. Internally, it has a link, it has a reference to a coffee object, right? So we're going to call that reference drink. So internally, there's a minus sign, so I guess it should be private, right? It has a reference to a coffee object, which is the drink that we are decorating, right? So every method that's in the coffee class, every public method that's in the coffee class, you now repeat inside of the decorator class, right? The implementation simply forwards the request to the underlying object. So drink dot drink. I probably shouldn't have called it drink. All right. How about this drink? There we go. Right. So I'm simply going to tell that coffee object to call its drink method. Right. So if we're decorating a cup of black coffee, right, that method there will end up calling the black coffee method here. And there's your decorator. Okay, so now we want an actual decorator. So I want to implement the foam, milk, and sugar classes. So, so do foam. Its superclass is coffee decorator. So there's our foam class. Oh wait, black coffee decorator extends coffee. I need a constructor. So public coffee decorator, right? So I need a constructor because I need to set this field here. And so it needs a reference to a coffee object, the drink. So this drink, like that. All right, now foam's going to complain. It's complaining because it doesn't have a no argument constructor, so we have to fix that. That's easy. Okay, and now we override our drink method. Okay, so all right, so I want to do super drink. Oh, sorry, I'm being a dummy. So I'm going to have to change. Oops, sorry. Where is, I don't want print line, I want print. So I don't want the new line character. So drink. So that's going to print out drinking coffee. And then we're going to add with milk to the end of the string, like that. Oh, wait, with foam. With foam, like that. And I'm going to do foam. I'm going to do the, sorry, busted control key. There we go. Okay, I'm going to do the exact same thing for milk and sugar. I'm just going to copy this class and paste it in. So there's milk. And there's sugar. Right, so milk's exactly the same thing. I'm just going to change this with milk. Right, and sugar, exact same thing. Change the foam to sugar like that. Okay, so what have we gotten so far? Well, let's take a look. So let's stick in a main method somewhere. So public static void main. Okay, I'm going to make a cup of coffee. And I'm going to drink the coffee. New black coffee, sorry. Okay, so you run that. And it says drinking coffee. Okay, no surprise there. Right, I'm now going to decorate my cup of coffee. So the way you decorate your cup of coffee is you do something like this. So C equals new foam. Pass in the coffee C. Right. Now you drink your coffee. Come on. Oops, drinking coffee with foam. Right. I can decorate the coffee yet again. Oh, Control Z. Right. So now I'm going to add some milk to my coffee. Right. And now I'm drinking coffee with foam and milk. Right. And I can add some sugar now to it as well. Right. And now I'm drinking coffee with foam and milk and sugar. Right. And so there's a simple example of how, so notice what's happened here, right? We started out with a coffee reference C, right? And every time we do something, every time we decorate the coffee, right? It looks like the type of C is changing each time. What's actually happening is you're making a new object, right? And you're reassigning your reference to point to the new object. But the new object has extra functionality added to it by the decorator, right? So we started out with a cup of black coffee. On the next line, it looks like we have a cup of coffee with foam. On the line after that, it now looks like we've got a cup of coffee with foam and milk. And then the line after that, it now looks like we have a cup of coffee with foam, milk, and sugar, right? And so there is a very simple example of implementing a decorator, right? Okay, so what's it going to look like for our task, right? Well, it looks exactly the same way, right? And so starting with our task class, right, we're going to subclass it with an abstract decorator class. Every task decorator, I guess we should call this task decorator, but anyway, inside every decorator is a reference to its task that it's decorating, right? And then you create whatever decorators you want down here, right, by subclassing decorator. Remember, every method that's in task, right, decorator will also have a copy of that method. It's simply going to tell that its internal task object to perform the method, right? The concrete decorator classes, they will override the methods, override the methods in task, so run and get status, so that they return the appropriate results for the decorator. So what do they look like? Again, in pseudocode, this is a Java-like pseudocode, right? So every decorator has a constructor, right? The constructor takes in a task to decorate. Right? Internally, it remembers what is that task that it's decorating. The run method simply forwards the run method to the underlying task. Right? Get status method simply asks the task for its status and returns that result. Okay, so let's make a repeater decorator. So this is a decorator that can repeat a task n times, or in this case, repeats times. Right? So what do? You make a constructor, right? You need a task to decorate. You need to know how many times do you want to repeat this task. Right? In Java, you would write super T. In other object-oriented programming languages, you would write something else. Right? Whatever it is you need to instantiate the superclass. Right? And then you set n to repeats. Right? Now run is dead simple. Right? I want to repeat the task n times, so you just have a little loop. Right? That runs n times. Each time you just call the superclass version of run. Right? What does the superclass version of run do? Well, it just forwards it. It forwards the run method to the underlying task. Right? So if you've got to walk across the map task that you run 3 times, you walk across the map 3 times. Right? So to repeat your amazing action 5 times, right? You make your amazing task. Object, right? And you decorate it with a repeater that repeats the task 5 times. Right? And so if you look at Unreal Engine, Unreal Engine uses a decorator to replace all of its condition tasks. So if you remember back in the previous lecture, which I have somewhere, oops, sorry. Okay, so remember our tasks. One of our tasks was a condition, right? And our conditions were leaf nodes that test some property of the game, right? Basically, they return true or false. Where's an example of one? Here, right? So here's a condition task that tests, is the door unlocked, right? If the door is if it's unlocked, so return, if this is true, task succeeds, right? Perform the next task. So Unreal Engine doesn't use these condition nodes, right? All of its leaf nodes are actions, and instead all of your conditions become decorators, right? And so you can easily create so in our framework, right, you can easily create an abstract decorator class that represents a condition, right? So abstract condition decorator, for example, right? Every time, so this thing here, so you now subclass this to implement the condition that you want. I guess I should show you how to do this. So it would look something like this. what's the best way to do this? Okay, so new class. So this is going to be an abstract condition decorator. It's going to be abstract, right? So this is going to, I don't have the thing it's extending, right? So it's going to be, sorry, /*. Sorry, this is going to extend task decorator. That's what it's supposed to look like. I don't have the task decorator class here, so. Okay, so you're going to do something like this, right? And so it's going to need a constructor. I picked the name that's much too long, sorry. Control. It needs a task to decorate. Ignore the error, it's because I don't have all the classes here. Oh, it now needs a, so the way you probably want to do this is as follows. So you want to create a protected method, Boolean, evaluate. This is going to be abstract. And there you can stop. Okay. So what you're going to do, so if you want to create some sort of condition like is an enemy visible or are you within some sort of proximity, right? You subclass your condition decorator, right? So you make a subclass of this. Whatever information you need to evaluate the condition becomes the fields in your class, perhaps, right? You override evaluate so that it returns true or false, right? And now your run method can simply do if this evaluate equals true, return success. Sorry, set the status to success. Otherwise, set the status to false. Sorry, to failure, right? And so you're going to now this evaluate method is basically a what the heck do they call them now? I forget. Your evaluate method is something that returns true or false, right? So it evaluates the condition you want to test. Oh, it's called a predicate. So that's basically a predicate of some kind, right? And all your subclasses that are conditions simply implement their own version of evaluate, right? And so that's one way you do it there. So Unreal Engine just uses a bunch of these. They provide you with a bunch of predefined conditions that are common to video games. I'm pretty sure that you can add your own by subclassing their condition their decorator class. Unreal's also a bit weird. So it's not just that they replace all your conditions with decorators. All decorators are in fact conditions in their framework, which is a little bit, which is quite different than what I talked about here. But that's the way that they chose to implement their framework. That's a bit funny that they did it that way. So if you look at the Unreal documentation, or if you look at its overview for their behavior trees, they say the reason they do it this way is because it's easier to read a condition that's embodied in the task itself, right? Rather than having to read a separate task beside an action that represents the condition, right? I guess a lot of people find this awkward to do. So this sort of thing here, right? So there's your condition, right? Which is leading to the next action. So in Unreal, that condition would be a decorator on this node here, and this would simply be an action, right? So is the door locked, yes or no, right? If the answer is no, this task never runs, right? So that's the way it works in Unreal. And so there's the decorator pattern. So that the decorator pattern, so it's a software engineering pattern. There's its application in behavior trees. Any questions about today's discussion? Okay, super. I think that's all I have for you today. We're very early today, sorry about that. I guess the next thing we're going to move on to is we're probably going to move on to physics, the physics engine stuff starting next week. So we'll talk about collision detection, how to detect collision detection, how collision detection actually or can work, and other physics associated topics. All right, so that'll be next week. I will have a reading for you later this week. I have to sift through the 124 midterms though, so that's what I'm currently occupied with.